Developers need the complete history of their code to fully understand how it works and the design decisions that went into creating it. Having the complete history available on demand and at the method level would make this information more accessible to developers. But how can this be done when the version control system only tracks line-level changes? Hi, I'm Nick, a PhD student in the Software Practices Lab at the University of British Columbia, and I'm presenting CodeShovel, an on-demand tool for robustly extracting method-level histories. CodeShovel is the brainchild of Felix and was part of his master's work in collaboration with Scheifel, who's currently a postdoc, Braxton, who is just starting his own master's, and Reed, who supervised the work. Let's start by looking at how CodeShovel would help during a code review. So here we can see a pull request that's been opened on the JUnit 4 project, and Mark is going to review the pull request. So Mark might begin by looking at the diff, and he can see that a method has changed, and he wonders if there are any prior changes to the method that might be relevant. So Mark switches to CodeShovel and first specifies the method. Then CodeShovel analyzes the code on the fly to find all the changes to this method. And so now Mark can see every single change that's happened to the method between the current commit and its introduction back in 2007, even across common code transformations. For instance, Mark can see places where the body has changed and where the signature has changed. He can also see where the method has been moved between files, and even when the method was renamed. So using this information, Mark can choose the commits that are most relevant for evaluating the pull request. Now let's look at how CodeShovel works. So CodeShovel iterates backwards through history from the current commit, searching for all changes until it finds the introducing commit. Now this would be easy were it not for the kinds of complex changes developers make to their systems. For instance, method signatures can be changed through renaming, or by changes to return type, parameters, or exceptions. Methods can be moved around within a file or moved to a different file. The file containing the method could be moved or renamed. A method's body can be changed in major and minor ways. And any number of these could happen in combination in a single commit. So how is CodeShovel able to follow the method under such extensive changes? Well, CodeShovel analyzes each diff using 4 heuristics that aim to track methods between commits, even as they've undergone common code transformations. For a given diff, CodeShovel first parses the file to extract all of the method signatures in the file, and then uses text-based similarities to examine method bodies. Let's walk through some of the commits made to the method in the pull request to get a sense for how these heuristics work. Many commits to a class file do not actually change the method, which is the case here. So the first heuristic CodeShovel uses is to look for exact matches within the class file, indicating that a method has not changed. So here the 100% similarity threshold is obvious, but we'll see for the next 3 heuristics that we had to determine the thresholds experimentally using a manually generated oracle. To account for the common case of small changes to the method, CodeShovel's second heuristic looks for a method with a very similar body within the current class file. Methods can also be moved between files, or the class file can be renamed. In these cases, CodeShovel applies its third heuristic, which looks for a method with an identical signature across all files changed in the commit. Finally, methods can also be changed when they are moved. To handle these complex changes, CodeShovel uses its broadest heuristic, which only considers method bodies and looks for the most similar body across all changes. In our evaluation, we found that CodeShovel was able to identify the complete histories for 90% of methods using these heuristics. Now, of course, CodeShovel isn't the only tool that's been created to track method level changes. we broadly classified these prior approaches into two categories. Industry-focused tools run on demand and use text matching to trace methods across commits. Two popular tools used in industry are GitLog and IDE-based tools like those included in IntelliJ. Research-focused tools, on the other hand, generally pre-process the entire history of the project, creating ASTs for every method at each commit. And several tools have taken this approach, with the most recent being FinerGit. We see CodeShovel at the intersection of these two categories. By generating ASTs for just the files that have changed and using text-based similarity to compare bodies, CodeShovel improves state-of-the-art accuracy while remaining fast enough for on-demand use. Now, as we saw in the demo, CodeShovel is able to trace through the example method's history through its 15 changes all the way back to its introduction. We ran CodeShovel on a total of 100 methods to see for how many of them it was able to produce complete histories. To do this, we had 4 people construct an oracle containing the histories of 100 methods from 10 open source projects. Now, making this oracle was quite a bit of manual work, and in some cases required exploring extra commits and having discussions to determine whether methods in earlier commits actually match the original method or not. So once we had the oracle, we found that CodeShovel was able to successfully track all of the changes to 90 out of 100 methods, giving a recall of 90%. Now, comparing with some of the related tools, we found that CodeShovel was able to find the complete histories for more of the methods in our oracle. Now, GitLog, for instance, fails to trace our example method once it has been moved to a different file, and overall is only able to handle a limited set of common code transformations. For our oracle, GitLog was able to get the complete histories for only 63 of the methods, giving it a recall of 63%. The next tool we examined was IntelliJ. It fared better on our example method, but still failed to find the commit that actually introduced the method. In this case, due to extensive changes made to the method in addition to the method being renamed. IntelliJ was able to identify the complete histories of 68% of the methods in our oracle. Finally, we look at the AST-based tool FinerGit. Now, while FinerGit was able to correctly identify the history of our example method, it was slower due to its use of pre-processing. In fact, because it had to process all methods and all commits, FinerGit couldn't actually process 4 of the 10 largest projects in our oracle, given 15 minutes and 16 gigs of RAM. So for the remaining 60 methods FinerGit was able to process, it identified the complete history for 39 methods, giving a recall of 65%. I should mention that the recall for these approaches is conservative, since we only counted complete and correct histories. However, all of the approaches were able to identify at least some of a method's history. For example, while CodeShovel only found the complete histories for 90% of methods, it was still able to find 97% of changes overall. In practice, these partial histories could still be quite valuable to developers, depending on what information they need to see. So that was a quick overview of CodeShovel, a fast and robust approach for extracting method-level histories. If you want to try out the demo for yourself on your own repo, the service is available at the first link. And if this talk has got you thinking about using CodeShovel in your own research, the full code, along with some excellent documentation, are available from Felix's GitHub account at the second link. In addition to the web service, you can also find command line and REST versions of the tool that can be easily incorporated into your own project and which support JavaScript, TypeScript, and Python. The repo also has our validation oracle with 100 manually verified Java method histories, and oracles for JavaScript, TypeScript, and Python are coming soon. We welcome anyone to use CodeShovel and to contribute pull requests to improve it further. Thanks.
Everybody for this last paper in this session on your histories and documentation. A paper out of University of British Columbia with me, just two of the authors, Nick Bradley and Reed. This is a paper published in the technical track, so we have full 10 minutes for Q&A, and also I should remind everybody that this is one of the recipients of the ACM SIGSOFT Distinguished Paper Award. So I wonder if the audience has already some question for the author of CodeShovel, Constructing Method Level Source Code Histories. Okay, well, maybe while the audience warms up a bit, I can start asking some of my questions that I have. Um, I was wondering if CodeShovel, or at least the implemented, that they can catch which a method is deleted and then re-added to the code base, uh, or commented out and then re-added to the code base.
Yeah, that's a great question. And I might need Reed on this as well because of his work on the algorithm. The
answer, unfortunately, is no, because the way we don't pre-compute anything, and the history is walked backwards through time. When the method was deleted, we would say, "Yeah, that was the original."
Oh, I see. So you stop at the first time, you don't find it. You don't look further in the past.
So,
I see.
And I think that's the only thing you can do if you want to do it online, because we don't pre-compute anything. So that is a weakness. But you know, it's interesting you ask that question, because there's lots of weird situations like that happen in practice.
Yeah.
Like if two methods turn into one method, like if two methods get refactored into one method, which of those old histories do you follow? Like, so there are. This is one thing in the evaluation of the paper where we found there was imprecision, because you know there are complicated things that happen in software development. But to your answer specifically,
humans are messy. Okay, we have one question from Peter in the chat. By the way, thank you so much for answering, Reed. Have you considered using parameters other than text similarity? In my experience, when we move a method, the calls to the method in that class and other classes move to point to the new class. When a method move is between packages, accompanies other methods, unless it moves to a utility class, behaviors, would that improve the results? And Reed, you're muted just in case.
Oh yeah, sorry, I was that's a really good question. I really appreciate it. I think you're absolutely right. Using, like, if a method moves from one place to another, but it still calls all the same methods, it's another really good hint. In our case, we found that it was just it worked well enough to not have to do that. All we really used the parser for is to identify method regions within the system, and then we just worked with the text representation. But that's a really nice suggestion. I'll admit one reason that we were hesitant to use too many structural features within a method was just to make it easier when we wanted to work with different languages, because now we work with Java and Python and Ruby and TypeScript and JavaScript, and the more languages you add, the more dependent you are on that parser being good and getting good static results there. So you're right. I think it would make it better, especially for a language like Java. But we haven't looked at that.
Okay, thank you for your answer. Is there more questions from the audience? I have also another small question regarding your experience the Oracle for the approach. It sounds like a lot of work, a lot of very painful work. Is there something you want to share about this? Lesson learned, I don't know, insights.
Yeah, I mean, it definitely was a lot of work. I don't know that there's anything to make it easier in the future. It was definitely a process where we had to sit down and just, because there was no existing benchmarks to go off of, right? So we basically had to start from scratch in that case. They're now available online, so hopefully we can save some other researchers some work. So I think we have them for Java and also for or we're coming up with ones for Python and JavaScript and TypeScript as well. So they'll be there, and so they'll be available for future researchers to save them some time.
That's cool. That's very cool. Okay, I think that the crowd has warmed up a little bit. There's a question from Hamad, who's asking, thanks for the nice presentation. How behaves in case the method extraction and method renaming. Okay, so those two actions combined. Extraction, refactoring, and method renaming.
Yeah, so again, because it's using this text-based heuristics, so these heuristics are robust across these changes. And so we did investigate robustness against each of these changes, and we were able to find that it does support these multi-changes as well. So it is able to go across these changes. Yeah. I don't know if you want to add to that, Reed.
To say that, just a bit more clear what Nick said, like that is the point of the algorithm, is specifically to extract method refactoring. So that is, and rename refactoring. That was the #1 use case that we wanted to support from the beginning. So yeah, that is the goal of the algorithm, really, and that's the biggest source of stored problems, along with file and package and directory renames, which are relatively easy for you to deal with if you deal with them intentionally, but are hard for users.
Okay, and there's another question from, she's asking, how is CodeShovel compared with existing program differencing tool? The history seems to be buildable purely by repetitively applying program differencing tools to software repositories.
Yeah, so I think the difference here is that with those kinds of approaches, you're going to have to process the repository. I mean, the goal here was to use simple heuristics and to be able to run in real time, basically, as a developer needs to. And so I think we looked at some differencing related work, and this was a more robust approach to that.
I mean, I think the performance aspect is hard to underestimate. I'll admit, when Felix started this project, I thought it would fail for sure. I thought that we couldn't compute a history in an online fashion, because you're right, what we are doing is essentially doing differencing, but online, like on demand. So the results are always up to date. There's no recomputation of a whole big repository, no incremental updates. And yes, it really is just a repetitive program differencing approach, but one that is tailored specifically to help us get method level histories.
So there's 1.5 minutes left to this Q&A. Remind everybody that after this Q&A, there's going to be a discussion room open to ask questions to the authors, and perhaps having a short demo. I don't know if Reed or Nick, you want to make a demo, take up a demo right now. You have exactly 1 minute, or you want to postpone that to the... We're going to do the demo now. You're muted, Reed. Reed, you're muted.
Running out of time, but this is CodeShovel, and we can literally just click on a method. So here, okay, these aren't pre-computed. This is literally cloning the repository, analyzing the method, and we can see here all the changes for that method. And for that, here we can see like this change on the first. We can see the modifier was changed, the file was changed. And again, all of these results are dynamically generated on the fly without any pre-computation. So same here, if we want to look at, for instance, this method, and then these left methods are just here for easy demo. They really are being computed on the fly, right? And we can see all of